circuits, we are always interested in finding current and voltage. So once we have current and voltage, then we can estimate power and other things. So in electromagnetic analysis, our interest is finding fields, electric and magnetic fields. And all our tools, whether Coulomb's law, Gauss law, Biot-Savart law, all these laws give us ways of estimating these fields. But the potential function, as we shall see, also gives a simpler method of estimating fields. So we will see that the derivative of potential function gives the fields. And we know that field is associated with force, for example, electric fields. How do we define electric field? Starting from Coulomb's force law. Similarly, magnetic flux density is defined starting from Ampere's force law between conductors.
Excuse me. Light intensity.
Yeah. Now, this potential function is generally a function of both space and time. And this is a very important point, that it is easier to calculate the fields from potential rather than directly from the charges. And that is, as we will discuss again, that is one of the important reasons for our introduction of potential function. So some preliminaries, of course, what is assumed is that I'm sure you recollect divergence, curl, and all those operations are important. We are not going to look at that, but phasors, a phasor representation of Maxwell's equations is something very important. So we'll have a very quick review of that. So as I said earlier, in any electromagnetic problem, whether antenna or radiator or just anything, our fundamental sources are either current density or conduction current density or charge density. And from this, we want to estimate electric field intensity or magnetic flux density. And then when we get to material electromagnetics, of course, we will also be interested in polarization and magnetization. So polarization is how a dielectric responds to an electric field. Similarly, magnetization is how a magnetic material responds to a magnetic field. And we also have the auxiliary quantities and auxiliary D and H. D is electric flux density and H is magnetic field intensity. And auxiliary is within quotes because, again, as I said, there is a diversity of views. There are some authors who believe that D, E, H, B, these are all fundamental. There are some believe that E and B are fundamental, whereas H and D are auxiliary, like that. So we know that electric flux density is D is epsilon E and magnetic field intensity is this. So our interest is always given sources to find E and B fields. Once we have this, then all other parameters can be estimated. Now, how do we do that? So our starting point is almost always conduction current J. But of course, we also find it convenient to introduce magnetic current density J. We will discuss as to why is the need for that. So starting from here, we want to discuss fields E and H, or B and E, and this can be done by a direct integration. For example, Coulomb's law gives us the electric field at a point. So by integrating over the volume of interest, it is possible to, in principle, to employ Coulomb's law to find the net electric field. But very often we find that that is much tougher than doing by introducing an auxiliary function called a vector potential. And A is what is called magnetic vector potential, and F is called electric vector potential. Of course, this needs integration, but much simpler integration. And once we have the vector potentials A or F, and then by a simpler differentiation, it is possible to get the fields. Once we have the fields, power and other things can be computed. So vector potentials are important in electromagnetics because they make the field estimation simple. So let us have a quick review of Maxwell's equations. So this is Gauss law, and this is Faraday's law, law of no magnetic monopoles, and Maxwell Ampere law. And we know that this is displacement current density. So I'm sure you recollect these equations. We will have to write this in phasor representation a little later. So for that, we'll have a quick review of phasors. So in electromagnetics, most of our analysis deals with this, what we can call periodic time function excitation. So periodic time function excitation means e power j omega t dependence is there. So since we know that the function varies periodically, it is not necessary to keep carrying on the time dependence all the time. So we can always suppress the time dependence for the time being, deal only with the magnitude and phase, and then there are ways of getting back the time dependence at any point of any time that we need. So one main advantage of phasor representation is that integral differential equations can be converted into algebraic equations. This is a very significant thing, as when we write on Maxwell's equations, see that. So actually, this is a very simple thing. We can start from Euler's identity and then like this. So when I write a parameter in terms of its magnitude and phase, that is called phasor representation. What I have done is e power j omega t term has been suppressed. So when I want the time domain representation, then I can multiply this by e power j omega t and get the real part. Now this part we are going to some examples. Actually, I have requested that the PowerPoint slides printout be made available to all the participants. It's already done, so that you can take notes or anything. So this is advantage. The time derivative can be replaced by j omega and integral. Actually, this is what we are going to make use of in writing down Maxwell's equations. So d by dt can be replaced by j omega in phasor representation, which is a big advantage. Okay, these are some examples. Now, so we write Maxwell's equations in phasor form. This is what we are going to use for subsequent discussion. So the tilde is used to denote the phasor representation. Divergence of E is this, and curl of E. This is Faraday's law. Remember that. So Faraday's law, and this is what law is this? Divergence of V is equal to 0, which is called, some textbooks don't give it a name. Some call it law of no magnetic poles. Some call it Maxwell Gauss law for magnetism, so on. And this is Ampere's law. So we have replaced dou by dou t by j omega and d by epsilon e. That's the constituent relation. And similarly, in Faraday's law, we have replaced dou by dou t again j omega. So these representations are going to be of help to us. So another theorem which is very important, fundamental to electromagnetics, is the so-called Helmholtz theorem, which says a vector field is neatly determined by its curl and divergence. So which means if the curl of a vector function is 0, divergence cannot be 0. Or if divergence is 0, curl cannot be 0. So if we are asked, okay, what can we tell about a vector function whose divergence and curl both are 0, you can only say that that vector cannot exist. So a vector field with 0 divergence is called solenoid. And it is quite intuitive because when divergence is 0, it needs to necessarily have curl. Curl represents a solenoidal property or rotational property. So a vector field with 0 divergence is called solenoidal, whereas a vector field with 0 curl is called irrotational or conservative. For example, in electrostatic fields, line integral of electrostatic field around a closed loop is 0. That is what is meant by irrotational or conservative field. So with these basics, I think we can get on to potentials from electric sources. So electrostatic potential we will not be discussing in detail because all the undergraduate textbooks deal with this. So work done by an external agent. So we start from here. So this is our this is work done. Work done is force into distance. So force is this. From Coulomb's law we know electric force is QE and this is distance. And it needs to be a dot product because the work done depends on the angle in which the charge is moved. So it is starting from this equation that we get differential electric potential, which we define as differential work done per unit charge and so on. Then it is easy to write potential difference between any 2 points and so on. So we know that electrostatic potential is independent of the actual path taken by the integration. So it is only decided by the endpoints. It is very, for gravitational analogy also, we know that. So so the result is independent of the integration part, and this we have to remember that this is an electrostatic field. So we are introducing electrostatic potential, and electric potential at any point with reference point being at infinity, we can write. And then starting from this equation, it is very easy to derive the potential due to a point charge, which can be written like this. Now, once you know this, it is easier to write the general equation for the potential due to arbitrary charge distribution. So that is what we are doing. So this is an arbitrary charge distribution, and rho v is the volume charge density. And it's important to remember that volume charge density is a point function. Or divergence and curl, these are all point functions. These are all defined at particular points. So one can write the electrostatic potential V at a distance r in terms of this. So it is not a complicated equation at all, because if you just look, when I integrate the volume charge density over the entire volume, what I get is the total charge enclosed. So, like if you just look at the analogy, so potential due to a point charge is q by 4 pi epsilon r, whereas potential due to an arbitrary charge distribution is in terms of its volume charge density. So when I integrate over the entire volume, I get q. Right. So it's easier to remember and say. So this is general charge distribution, and it is very easy. And we, as we said earlier, one of the particular usefulness of potential functions is that they enable easier estimation of fields, and we can very easily determine an equation that links potential and electric field, which is quite a simple one. So for one-dimensional fields, we can write EL as minus negative derivative of V over L. L is the displacement. So of course, we know that three-dimensional derivative is del. Del operator gives three-dimensional derivative. So while this equation holds for one dimension, for three dimensions, I can generalize this expression. V is equal to minus gradient of V. This is important. And we have to remember that this holds only for electrostatic fields or also for quasi-static fields. So quasi-static means when for example, in a capacitor, when the fields are slowly varying, or for static fields, only this equation holds. For time varying fields, it is important also to include the contribution of magnetic vector potential. Am I making some sense? Am I going too fast? So how do we introduce magnetic vector potential? So divergence of B is equal to 0, that is Gauss law, whatever, or law for no magnetic monopoles. So divergence of B is equal to 0 means B has 2. Curl of B cannot be 0. Okay? And vector analysis tells us that when a vector function has a non-zero curl, like curl of B is not 0, so B has non-zero curl, then that vector can be written as a curl of another function. So, which is B is equal to curl of A, and A we call vector potential. It is not arbitrary, because if you just look at, in the case of electrostatic fields, we found that the potential minus del V gives the potential. So, when we are able to write B as curl of a function, curl of another vector A, we understand that it can also be called by a similar name, by analogy. So that is what we call magnetic vector potential. And of course, we know this constituent relation B is equal to mu h, that is curl of A. And one problem that particularly students who are just beginning to study electromagnetics, engineering students, when they see a lot of equations in the textbook, it can often be repulsive. But if you take the time and then see that, okay, no, I can understand this, if you take that kind of positive approach, you will find that it will make a lot of difference. So all these equations, when somebody sees all these, oh, what is this divergence curl, it's all annoying. But it won't definitely be annoying from me when you just, pull down and then try to approach it one equation at a time. It will be very interesting. Try this approach when you study next time. B is mu h, this curl of A. And obviously, I can write h as 1 by mu like this. Now, we look at static case, where the field is not time varying, and curl of B is mu j. What equation is this? Ampere's law. Ampere's law without the time varying factor, dou d by dou t. Now, of course, here we have already defined the vector potential like this. So, B is curl of A, and we also use this vector identity, curl of A is equal to this. And from there we can get gradient of divergence of A minus is equal to this. Now, this is a very interesting aspect of electromagnetism. We arbitrarily choose divergence of A to be 0. There is one choice we can make. There are many other choices, and this particular choice is called Coulomb gauge. And of course, there are people who differ. Some people say Coulomb gauge because when we look at later, this Coulomb gauge predicts instantaneous potential. But there is retarded potential. I hope you recollect it. Potential at a point due to a time varying charge distribution is retarded, whereas Coulomb gauge predicts instantaneous potential. But then the fields predicted by Coulomb gauge is just as correct as that predicted by any other potential gauge. So we choose divergence of A is equal to 0 so that you are able to simplify this equation as del square A is equal to minus mu j. So what this equation gives us? This equation, see, we have defined A, which is magnetic vector potential. And this equation gives us a way of calculating A from J, because we have to remember that it is J which is our source. J is the source, as we said earlier, in electromagnetic problems, J or rho, they are our sources. So whatever we estimate should be able to be, any estimation should be done starting from the sources. So having defined A, obviously we need to write down how A can be related to J, and that is what we have done, starting from Ampere's circular law for static case. Del square A is equal to minus mu j, and it is possible to see that the solution for this second order differential equation is this. Now, dynamic case, time varying case, and here we start from curl equation, and this law is, what law is this? Faraday's law. Okay. So curl of E is equal to minus j omega. I have replaced dou by dou t in time representation, and B is replaced by mu h. So this is Faraday's law. Now, having defined B earlier, I can write minus j omega curl of A. Right? And now this I can just rewrite as, I just bring the right hand side to the left hand side. I can write like this. And again, vector analysis tells us that curl of gradients of any function is 0. So now, okay, this is my first step. And then I know this vector identity, which is curl of minus. Why we introduce minus? No need. Actually, the identity is curl of gradient of a scalar function is 0. Okay? And I just introduced for convenience so that I can be consistent with my earlier relation. E is equal to minus del B. So we can use this vector identity and see that E plus j omega A is equal to minus del B, which translates to E is equal to minus del E. That is the part we have already seen, minus j omega. Okay. So this is for the time varying fields. So again, it is important to recollect. Suddenly, when you look at this equation, why, what is E, B, J, and all, we are trying to say that fields can be determined using potentials. And here what we have done is to write E in terms of the electric scalar potential and magnetic vector potential. For static case, electrostatic case, for electrostatic case, we just get V is equal to minus 1. Now, what is wave equation? Wave equation is a second order differential equation. And it can also be very easily obtained. We just take curl of on either side of 1, which is this. And again, vector identity, it all reduces to this. For a homogeneous medium, in electromagnetic textbooks, two terms, homogeneous, isotropic medium. So it's important to be able to distinguish. So a homogeneous medium is one where the material properties are same everywhere. Isotropic medium is one where all directions and the, yeah? Yeah, the dielectric property, electrical property is independent of the magnitude and direction of electricity. Because there are crystals where, depending on the direction of the impinging electric field, dielectric constant can be different. So isotropic media means materials which display same dielectric properties or magnetic properties, irrespective of the magnitude and direction of electric field. So for a homogeneous medium means I can just bring mu out, so like that. Now, okay, we just keep it there and then recollect Maxwell Ampere equation, which is this. Now what we do is we equate this equation and this equation and get this. Then I think we can go through the material to get this. And I would suggest that those of you who are not very comfortable do work out the simple substitutions and all, because it will increase your confidence level, which is very important. So we substitute like that and we get an equation which is not very simple. So again, we make another choice, which is called Lorentz condition. We choose divergence of A as this, just for convenience, so that we can simplify this equation as. So this is a wave equation for A for time varying fields. So a solution, obviously, it has to be in terms of retarding potential. A solution can be obtained like this. And we can see that the Lorentz condition or Lorentz gauge, which is this, Lorentz condition can also modify 11. 11 is, what is 11? This. So, this. So now, once we know A, H can be calculated very easily because curl of P is equal to curl of A. And then E can be estimated either by using 19, which is this, or by using Maxwell Ampere equation with J is equal to 0. So, and again a phrase that is very common in electromagnetic papers, source-free region. So, normally when we estimate fields in far field zone, sources are 0. Source is, for example, a mobile tower, an antenna which sits kilometers away. So sources are not don't exist in the area in which we are considering or calculating the fields. So when we consider Maxwell Ampere law with source 0, then J is equal to 0, it is also possible to calculate the electric fields. So this is these two potentials. Now, as I said, we also have potentials that are defined starting from magnetic sources. And as far as we know till now, magnetic sources do not exist. But why is it that we find it convenient to introduce fictitious magnetic sources? There are several reasons from whatever I could find. One is when we consider the analysis of aperture antennas, the horn or parabolic aperture. So let us look at this antenna. So we know that radiation is essentially in the forward hemisphere. So, of course, the fundamental source of electromagnetic radiation, whatever form it appears, is the time varying charges. So here we have time varying charges on the walls. Okay? But then intuitively, it will be better if you could treat the aperture of the antenna, which is a the opening as the real, source of radiation rather than the walls. It gets more tricky if you were to integrate the charges and all. So it would be convenient if you could define some equivalent sources at the aperture and do our radiation analysis starting from there. So that we do by introducing magnetic currents. So this is one usefulness. Then symmetry considerations. When we look at Maxwell's equations, from the field perspective, symmetry is there. For example, a time changing Faraday's law tells us that changing magnetic field produces a changing electric field, whereas Ampere-Maxwell law tells us that changing electric field produces a changing magnetic field. But in terms of source, there is dissymmetry in Maxwell's equations, because on the one hand we have divergence of B is equal to rho, whereas divergence of B is equal to 0. So it would be obviously more pleasing to have a symmetrical set of equations. Man always looks for symmetry. So from that point of view also, it may be helpful to introduce magnetic charge. So in that case, Maxwell's equations, obviously you can see that the symmetry is preserved here. So divergence of B is rho. So we have introduced fictitious magnetic charge density, and similarly fictitious magnetic current density. So this presents more symmetry to Maxwell's equations. Of course, it is not only from the viewpoint of symmetry, because as far back as 1931, Dirac proposed that like charge is quantized, charge is quantized, and we have not found as to why charge is quantized, though we take it as a fundamental law. But Dirac proposed that if we could find even one magnetic monopole, that could be used to explain as to why charge is quantized. That is one thing. Another thing, of late people are talking about grand unified theories of weak electromagnetic and strong interactions. And an important component of this theory is also magnetic monopole. So theoretical predictions are, we shouldn't be very much surprised if magnetic monopoles were to be proposed or suggested. Then there is another reason for introducing magnetic sources, which is what is called duality principle. And now we know that electric circuits, when we look at these circuits, these two circuits are dual circuits. Similarly, an electric dipole and electric loop are dual circuits. So analysis of one can be easily extended to the analysis of another if it could come up with, if we found that those two circuits are dual structures. So now let us consider an electric system. Electric system means J is the source in materials like this, and Maxwell's equations are like this. There is no magnetic source here. So this is Faraday's law and this is Ampere's law. Now we consider a magnetic system in which electric sources are 0. J and rho are 0. Whereas we have fictitious magnetic current source like this. For this system, Maxwell's equations can be written. It's very easy to follow this. And this is Ampere's law. J doesn't exist, therefore J is 0. Whereas the Faraday's law, curl of E, we have a magnetic source, therefore that is an addition to Faraday's law. So these two systems of equations are dual systems. And that, how can we see that? It is possible to get one set of equations from the other by replacing Jm by J epsilon 2. So these are dual structures. So dual structures, as we have seen, this are in the case of dipoles. And I think any antenna textbooks, they present this method. So this is another reason as to why it will be convenient to introduce magnetic sources. So there are three reasons that we have cited. There could be more. Whatever I know is what I have. So one is aperture antenna analysis. So it is more convenient to introduce some sources at the aperture. Obviously, this aperture cannot support conduction current. So we can call that magnetic current. And another is symmetry in Maxwell's equations. and thirdly, duality principle. This we can now define galactic vector potential. So, auxiliary electric vector potential, the way we discussed magnetic vector potential, so we use Maxwell's equations with electric sources. So, if you start in a similar fashion with the magnetic sources, it is possible to come up with this. Actually, if you just compare this equation with that for A, then they can be easily found out to be analogous to each other. So, it is what we need to do is to start from Maxwell's equations with magnetic sources. And the way we wrote earlier B as curl of A, it also emerges that we can write B as curl of F, the way we did for electrical system. And it is important here, see, having defined magnetic current density, how do we write it down? And this is an important boundary condition. Of course, this I'm sure you would have at least a vague recollection of. So, across an electric boundary, we have the tangential magnetic fields being discontinuous by Js. Js is the conduction current density. And similarly, across a magnetic current sheet, what is a magnetic current sheet? Like, for example, the aperture of a horn or a reflector, for example. So, the tangential component of electric fields is discontinuous by magnetic current density. Like that. So, in situations where we have both electric and magnetic forces, we can get to the total radiated fields by adding contributions due to both the sources. Now, magnetic scalar potential is another. Again, under static conditions and under source-free conditions, curl of H is equal to 0. And the way we discussed earlier, curl of gradient of E is equal to 0. Therefore, we can write H as minus gradient of Vn, where Vn is called the scalar potential. Again, if you recollect, initially we said that potential is a function whose derivative gives a field. So, whether it is electric vector potential or magnetic vector potential or electric scalar potential or magnetic scalar potential, it is derivative, because whether it is gradient or curl or divergence, it's all derivative. So, this derivative gives fields. And of course, in this case, Laplace equation is Laplacian of Vm is equal to 0 is obeyed just as in the case of electrostatic fields. Now, what about the physical meaning? Do vector potentials have physical meaning? There are contradicting views, but it is important to define what we mean by physical meaning. If by physical meaning, if I say that something is physically existing only if I can see it, obviously much of electromagnetics doesn't exist. Electromagnetic waves we cannot see, isn't it? So, it is important to give a broader definition to what is the meaning of physical meaning itself. So, this is Giuliani in 2010. He defined like this: a theoretical term has physical meaning if it cannot be withdrawn without reducing the predictive power of a theory. And in that sense, obviously, vector potential is quite physical, because if we remove vector potentials from electromagnetics, it would make it more complicated. Not that predictive power will be withdrawn, but at least it will make it very complicated. In fact, Maxwell treated the potentials as having physically meaningful functions. But Heaviside and Kurtz, they reversed the trend, and they told they are auxiliary functions. In fact, I have not seen engineering textbooks where the potentials are presented as functions having physical meaning. Because my understanding is that most of the engineering electromagnetic tests, they present as something auxiliary or secondary functions. Then there are views. And then Feynman in these lectures, he has told that no, vector potentials have physical meaning. And in fact, at least in quantum physics, potential functions are not just auxiliary functions. But then, as far as I have seen in engineering electromagnetism, we treat vector potentials as largely auxiliary.
Radiation. That is source of importance of without
we cannot understand. It is very significant, definitely. Like when we presented, starting from sources, how do you get fields, vector potentials, of course, make field estimation simple. It's fine. So a real field is a mathematical function we use for avoiding the idea of action at a distance. It's very electromagnetics. When we look at it in context, it is an enormously interesting discipline. When we just read a textbook mechanically, it may be boring. Definitely, it could be boring. But then, see, for example, this has a political connotation also. I think I presented when I discussed displacement current. We had continental and British traditions some 200 years back. So continental tradition, they were comfortable with just action at a distance, whereas British people, British scientists wanted what is called a field primacy approach. So A has physical meaning because it is used for avoiding idea of action at a distance. But these are all interpretations. And if there are any of you who get confused, how can there be contradictory opinions? But such opinions are not unusual in electromagnetics. Several cases, like we have seen, potential functions are gorgeous. Actually, some people, when I worked on my paper on displacement current, I corresponded with Yudjin and Jackson and all. So they have different views. Yudjin rejects the Coulomb's gauge, whereas Jackson says, okay, what is problem with the Coulomb gauge as long as it provides the correct fields. So views are different, and displacement and dimensions, whether dimensions are real or not real. There are different views, and very recently I came across these two interesting papers in American Journal of Physics. And Hobson wrote, there are no particles, this refers to wave particle duality. And Hobson wrote, there are no particles, there are only fields. But then there was a rejoinder just later that there are no particles and there are no fields. And according to this author, it's all mathematical constructs. So there are people, so my approach to electromagnetics is, I think, partly we should be prepared to work only with the equations without bothering about physical meaning in every single step. It gets really complicated. But wherever it is possible, wherever it allows physical interpretation is fine. When it doesn't allow, I think it is better to enjoy the beauty of mathematics rather than trying to look for physical explanation. That is my stand. But again, you should and you are most welcome to take your own stand. That is what makes electromagnetics really beautiful to me. And obviously, several textbooks, beautiful textbooks, and then apart from that, these are the papers that I have consulted. There are some, actually, I did not make, there was no time make an exhaustive list of papers I used. You can just see, these are all very interesting papers. Yeah, all this. So this is what we have done. And one thing that I always drive in my classes is electromagnetics is a fascinating subject because it gives scope for diversity of views and approaches. It is not a rigid discipline where okay, you have to do things like this or you have to do things like that. So I find electromagnetics to be intellectually stimulating when we try to learn it in context. So with that, I'm not sure whether I have really rushed through anything. I don't have a good feeling at the end of my lecture. But whatever it is. So any comments, questions? And I appeal to students, even if you're not having questions now, later I want to discuss with you. I mean, if you find electromagnetics interesting, please tell me. That will be a delightful thing. If you find it boring, then I can try to give some tips as to how I made the subject little at least interesting to me. So particularly the student level interaction, I want to kind of a lot. So if there is anything that you want to say now, I didn't know. how the magnetic current density
चलना ही नहीं.
helps with application of duality principle. Ah, yeah. It's not clear yourself. So, this is the question.
Dr. Selvan, will you please make the question audible to the other people also?
Yeah.
Meanwhile, a mic will be coming to the participant.
Yeah. So the question was relating to the duality principle. Actually, when I told there are three situations that make I have. So how duality principle? Yeah, as I told. So as I told, the electric dipole and magnetic dipole are duals, isn't it? So a loop antenna, a small loop antenna, is a magnetic dipole. So if you just look at how the radiation fields of a small loop antenna can be reduced, by analogy to the field equations for electric dipole, it is possible by just making transformation. So without having to go through the entire derivation all over again, it is possible to use the equations for one to get the equations for another. Magnetic loop, which is a magnetic dipole. For example, like that, so whenever we find that a structure is a magnetic dual of an electric system, we can use the equations of the electric system.
If there are no queries, we would like to convey our.
Yeah, just one. Yeah. Okay, I will tell. The question is, this question relates to the symmetry considerations. We said that divergence of B is equal to rho m, which introduces symmetry into Maxwell's equations. The question is as to how. Now, this divergence of B is equal to rho. But in this case, divergence of B is 0, isn't it? So that means there is no symmetry. Symmetry is here on the right hand side, we have a source term. Here we don't have a source term because magnetic monopole don't exist, isn't it? Now this rho m is magnetic charge.
You are telling me that whatever these will presents a symmetry, it represents a dissymmetry.
Yeah, correct.
Look, how you are.
How we are saying that? And that is, see, if you just look at this equation with like this is 0.
Yes.
Now, see, with reference to fields, like there is symmetry,
Yes, sir.
right? This is clear. Now, with reference to source, because see, this is the source term, right? I can say the source term. In this equation, we have a source on the right side. Whereas this equation, the source is 0. You know? Source is 0. So now we just deliberately introduce the source term, and this is a magnetic monopole, which is not known to exist. But we say if you introduce a magnetic charge density, which corresponds to a north pole or south pole existing separately, then symmetry, like in terms of both source as well as field terms.
That's why you already do GM.
Yeah, exactly. That is magnetic current density, and this is magnetic charge.
That was a neat introduction to electromagnetic theory from Dr. Selvan. We would like to convey our appreciations in our conventional way by clapping our hands. Just to be on the lighter side, and not to be quoted, I would like to add a small lighter incident which happened in one of the symposiums. One group of persons was asking, one person from a group was asking, electric potential or potential difference or voltage, it's a measurable quantity. I have an voltmeter, I can measure it. I can't measure vector magnetic potential. And why should I accept a vector magnetic potential when there is no possibility of measuring it at all? All other quantities that have been introduced have been accepted by this group only after measurement was done. What about vector magnetic potential? Who will make a measurement? How do I measure it? So till a measurement is made, why should I accept that there should be a vector magnetic potential? I mean, all this on the lighter side, please, not on the technical. So the other group said, if you do not accept the possibility of a vector magnetic potential, you are saying that it is wrong. Why are you saying that it is wrong? I will say that this group said it is wrong unless and until it is proved right experimentally. The second group, which was advocating for vector magnetic potential, said, all right, until and unless it is proved wrong, it is right. And it has not been proved wrong. It has been accepted as a right quantity. It has been used for antenna theory and techniques in an enormous way. And the build-up for that was beautifully given by Dr. Selvan. Thank you. The next speaker would be, this is an anecdote we use in the conventional undergraduate classes to make the discussions after the laborious derivations and all, to make the class lighter and to have a feel of what they are doing and let them feel about potentials also. I'm very happy that potential functions are beautifully brought out by Dr. Selvan. The next speaker would be Professor Ramesh Garg, our teacher at IIT Kharagpur. He will be yeah. Please. She will be introducing the teacher, Professor Garg, to you, and he will be speaking on FDTD techniques, which are also very popular nowadays in the electromagnetic theory and antenna theory and techniques. Please.
Professor Ramesh Garg is an eminent professor who has contributed a lot in the research area of electromagnetics and microstrip patch antenna. He is a fellow of IEEE and also has published various international and national journals, including IEEE transactions and magazines, IEEE journals, and reputed conferences also. He has also written text and references books and also a member of editorial board of various national and international journals, member of RF and Microwave Computer Aided Engineering, member of IET of Journal of Education. I request sir with the kind permission of session chair to proceed for the session.
I request Professor Garg. I am also curious to that.
Have taken the liberty to expand its scope. The first part of it will talk about the computational techniques in general, that will be for about 15 minutes, and the rest 60 minutes, because I think that what's written over there should be around total 75 minutes start. Plus 60 minutes will be for FDTD tutorial. Let's go to the next one. This is the layout of the presentation. That what I said was why computational methods. That is the first part. Second, basics of computational methods. And third is FDTD basics for one-dimensional analysis. Why I'm talking about why computational methods, basics of computational methods, I think will become clear. If you go to the next slide, I'd like to answer this on why computational methods in an alternative way. Why not analytical methods? You know, there are analytical methods available, there are computational methods available. Okay? Computational methods are very same things. while analytical methods have been there for a very long time. And I like to answer this question of why computational methods through, in an alternative manner, why not analytical methods. Let's go to the next one.
Next.
First of all, we define the analytical methods. The analytical methods, the main thing over there when we apply these methods are that we are supposed to know the physics of the problem. That is the first thing. And second is the form of the expected solution also should be known. Only we can attempt the analytical solution. And this is possible only for simple problems. So for example, you work with rectangular geometries or circular geometries, so method of separation of variables, etc. And if it is a complex problem, you run into the real complexities. Can we go to the next one? Here I've taken a very simple example. So for example, if there is a plane wave incident on an air dielectric interface, how do you attempt? It's shown there that on the left side there is a air medium, on the right side there is a dielectric. And basically we are trying to solve a wave equation subject to the interface condition over here. And we can write down the solution, attempt the solution only if we know the physics of the problem. For example, here it's written there that the solution, electric field in this case, is a sum of two terms. One is the incident wave and the other is the reflective wave. And since it is a plane wave incident, so the plane wave solution is there for the incident one, and the gamma is the reflection coefficient. So what I was trying to say, that in analytical methods, one need to know what is the physics of the problem. So for example, here we know that there is an incident wave and there is going to be a reflective wave. And we know the expected form of the solution, that for a plane wave, it has to be that form. Okay? E raised to power minus jkz, and the other one is the reflected wave with the exponential jkz. That is the crux of the problem, so the analytical methods are concerned. And that also puts a limit on the versatility or not versatility of the analytical methods. That is, you can apply it to the simple problems, not to very complex problems. It becomes very difficult. You can go to the next one. Some of the analytical methods are given over here. Most common ones: method of separation of variables, Green's function-based methods. Sorry. Yeah. Okay. So first method of separation of variables, Green's function-based method. There are some conformal mapping method. We carry out the analysis in the spectrum domain when we are working with the layered dielectric geometries and the mode matching mapping. We add some more of them. These are the very common analytical methods. And the limitations of the analytical method, as I said earlier, is applicable to the simple geometries or their combinations like rectangular, circular ones, etc. It's a combination of those ones, such geometries, to which these analytical methods can be applied. One need to know the physics of the problem. And other limitations are the geometry should be homogeneously filled, although one can use the equivalence principle to convert it into an equivalent problem with homogeneous dielectrics. Okay. You know, there are various types of limitations are there in analytical methods, and there are various ways to take care of those limitations, like equivalence principle are there. There are various types of principles are there, which are evolved over time and makes the applicability of the analytical method to larger number of problems. Okay. Then there is the about the boundary condition, they should be either homogeneous boundary conditions like Dirichlet, Newton, or mixed type. Inhomogeneous boundary conditions cannot be taken care of. The solution is mostly partial and not total because it is difficult to include the effects of various couplings, higher modes, radiation, etc. in the solution process. So these are the limitations of the analytical methods that answers our question, why computational methods? So because of the limitations of the analytical methods in terms of, let's say, arbitrary shaped geometries cannot be taken care of. Homogeneity of the dielectric is also a limitation. Inhomogeneity of the boundary conditions is a limitation. And the solution is not an integrated solution. And that's why the computational methods are become more important. That's the advantages of analytical methods. What we get is that the solution process is efficient and may produce design information also. The solution can be used for benchmarking of computational based solutions. Okay? The range of problems that can be solved is large in the sense that it can include concepts like image principle, reaction theorem, and geometry specific problems. So here it makes a large difference. So for example, when we talk about the computational methods, mostly you are solving problems which are based on the geometries. But if you talk about image principles or theorems, equivalent theorems, etc., there is no such thing in the computational methods. That distinguishes one from the other. Now we come to the computational methods. These are some of the most common computational methods. One is finite difference frequency domain method, finite difference time domain method, finite element method, method of moment, boundary integral equation method, transmission and matrix method. These are a number of methods that are available over there, and these are the advantages as we learn from this one, that the analysis method is applicable to arbitrarily shaped geometries and the dielectric fields, homogeneous or inhomogeneous. It provides complete solution, that is total solution, including the effects of wave guidance, coupling, higher mode, radiation, and scattering. Everything is included in there in the solution process. Yeah. I won't say that. I would say that it's not a part of. You use some analytical part of it, like you need to find out the Green's function. Only then you can go ahead with it. Pardon? No, you can say the method of moment is using some part of the analytical method for the solution process. But I won't say that it's totally an analytical method. Okay? That way we can say that in almost all the computational methods, you use some of it. Even in the finite element methods also, you use some of the analytical processing. Okay? Analytical pre-processing is there in most of the computational techniques. Okay? Then you can use the parametric based analysis to obtain the design information from the computational methods. Because the computational methods as such are the analysis method. They don't give you straight away the design information. But you may get this one, you can carry out the parametric analysis, and from there you can extract some design information. The development of computational methods are highly mathematical, but their usage is not. As you know, these days, most of the students or research scholars just buy or maybe get the software from somewhere and start designing it. And FTDD is well suited for developing instructional material because it simulates wave propagation in time, and the animation associated with this method makes the subject interesting. That's another aspect of FTDD. The pulse propagation, see, this is the best part of it, so far as FDTD is concerned. The pulse propagation in time and associated reflections at mismatches may be used to understand the physics of the complex problems which may help with the modeling design process. Okay? And the computational methods are going through a phase of development, and it may lead to progress in teaching also if the two are linked together. But there are limitations of computational methods, as we say, that they are applicable to only geometry-specific problems. Not very general things like if you want to, let's say, formulate the image principle, if you want to formulate equivalence principle or reaction theorem, what do? You can't do anything in the computation method. They are only specific problems can be taken care of. That is basically for the product design. That is the limitation. These methods are computational intensive, that we already know, and they are limited to geometries of the order of wavelength. But now, using the hybrid methods, this limitation is being taken care of. The solution may be nearly exact. We cannot say that the solution can be exact, whereas in the analytical methods, you can get the exact solution also. But here, in the computational method, we can never say that the solution is going to be exact. It's going to be, because of the various approximations over there, it's going to be nearly exact. And there is a possibility of a spurious solution. That's also possible. So one has to be careful while accepting the solution from the computational method that this is the only solution, or the right solution. So there is a possibility of spurious solution also, mainly because if the boundary conditions are not properly met over. Yeah. I didn't want to say that it is approximate. No, people normally we say that it is approximate, but we can make it nearly exact by having more and more number of elements, or smaller and smaller size elements. You can approach that limit. In the limiting case, you can say that it can become an exact solution. Okay? That's it. Now, I'm coming to the solution procedure. The main reason why I'm introducing over here is this, that a few years ago I was going through a IEEE APS magazine, and one of the research scholars has asked this question, that given a problem, given a statement of a problem, how do I formulate the solution? And I think lots of research scholars have a similar problem. That you are given a problem or a geometry, like it could be a circuit, it could be an antenna. And let's say in the case of a circuit, you want to find out the S parameters. You are asked to find out the S parameters. But how do you formulate the problem so that you can find out the solution? Now, the first thing in this process is whether we apply it to right now I put it for the computational methods. The same more or less holds for the analytical methods also. Thinking is that whatever be the problem, statement of the problem given to you, basically it is a mathematical problem. You have to treat it as it's a boundary value problem. You have to treat it as a mathematical problem. And once you understand that it's a mathematical problem, naturally you have to find out the corresponding differential equation or integral equation to solve. Okay? So the first step is select or formulate the governing differential or integral equation for the given problem. That is the starting point for any problem in electromagnetics. Second step is that create the geometry for the problem and discretize this geometry into cells. That is the heart of your computational techniques, the discretization of the geometry. And similarly, basically it means you are discretizing the differential equation or the integral equation to obtain the governing equation for a cell. The next part is, the next step is, that is what we describe as the discretization. That is, basically when we say they discretize the geometry, we are dividing the given problem into a large number of smaller problems with regular shapes such that the solution of each of these problems can be formulated relatively easily. Discretization basically in a sense, philosophy means like this. A bigger problem is being divided into a number of smaller problems. Then formulate the solution, general solution. You cannot find out the specific solution of that governing equation for this set. Because when you are dividing a bigger geometry into a number of smaller geometries, most of these smaller geometries don't have any boundary condition. So naturally what you are formulating for these geometries, smaller geometries or sets, is a general solution. It cannot be a specific solution. And then apply the solution over each and every cell of the given geometry. Then you have to assemble the solution from the various cells. That is, continuity of the solution across the cells is introduced while assembling the solution for various cells. Okay? And this will result in a matrix equation like B is equal to XA. Next, you apply the boundary conditions. That will be, where the boundaries are there, the boundary conditions are applied for the given problem to specify some of the unknowns, and finally it will lead to the specific solution or the unique solution for the problem. And the solution A, whatever you get, is basically either the current or the field distribution for the given problem, and using this distribution, we can find out the characteristics of the devices, such as S matrix, radiation pattern, RCS, etc. So these are the various steps. In fact, the steps for the analytical solutions are similar. Only thing is that there is no discretization process in the case of analytical solution. Solution process difficult. Okay. This is the flow chart. Same thing in the flow chart form. The problem at hand. Select or formulate the differential equation or integral equation or integral differential equation. Discretize the geometry into cells and apply the governing equation at each cell. Assemble to obtain the matrix equation, apply the boundary condition, and work out the solution of the matrix equation. Okay? So these are the various differential equations of the electromagnetics. Maxwell's differential equation, those are the basic ones. From there you can derive the Laplace equations and the Poisson's equation. So when you are working with electrostatics or magnetic statics, that is, you are given a problem, and from the problem you can make out whether you are being asked to work a static problem or it's a full wave problem. And if it is a static type of problem, then it will be either belong to Laplace differential equation or a Poisson's type of differential equation. Otherwise, it will be a homogeneous wave equation for the full wave solution, or it will be an inhomogeneous wave equation. Okay? So it makes your job very easy. That from the statement of the problem, one should be able to pick up the right type of differential equation. These are the Maxwell's equations. I have not given in detail. So mathematically, so you have this in left side, you have the Laplace equation and Poisson equation, homogeneous and inhomogeneous wave equation. But when it comes to, so far as differential equations are concerned, they are very general. Okay? But when it comes to integral equation, or the solution of the integral equation or integral differential equations, they are specific to a problem. The integral equation is not very general one, because in the integral equation we include the effect of the boundary condition also. So you cannot write, just like we have seen that for the differential equation type of problem, you can put it in terms of Poisson equation like that. But for integral equation solution or differential equation solution, you have to derive it for that given problem. You cannot say that this integral equation can be applied to the various types of problems as such, because the boundary conditions is going to differ from one problem to the other. So the integral equation is going to be different for different problems. No. Because the thing is that in the integral equation, when you are formulating it, you are including the effect of the boundary conditions, and in most of the cases, your Green's function is going to be different for different problems. Because of this boundary condition being different, you cannot use the same Green's function for different problems. That's why the integral equation you cannot say in general that for these type of problems you can use this. No. Differential equations are very general type. Yeah. These are the cells, basic cells we use for the discretization. One-dimensional case, it could be a straight line or a curved one. Two-dimensional, it could be a triangular type or a quadrilateral type. Three-dimensional problems, we could have tetrahedrons or bricks, etc. This is the discretization we have shown for a circular geometry. Although circular geometry is very easy to analyze using analytical methods, but when it comes to computational methods, it's a very difficult thing to analyze in the sense it requires large number of cells to reduce the error or the, okay? Yeah. Now we are coming to the second part of it, the basics of FDTD. So up till now I have not tested your knowledge, but I think we are talking about the tutorial. Maybe I'll ask you a few questions, hoping that you have come prepared with FDTD. And we are going to deal only with the basics. And it's very easy to understand the basics if you are working with 1D problems, and easy to extract the same concepts to 2D and 3D. That's why I've taken 1D. So basic thing of what happens in FDTD, I'm trying to understand through a pulse propagation in a loaded transmission line. Because when you work with FDTD, you are launching a pulse, and when this pulse propagates in the geometry you are trying to analyze, it moves from one point to the other slowly, and then at some places there will be reflections, etc. So after to and fro reflections, number of times, then there is a steady state field distribution in there, and that's what you try to arrive at. Although the same process is there in the case of, let's say, other techniques also, but here in FDTD you get the animation, that how the wave is progressing from the initial beginning at t is equal to 0 to when it comes to the steady state, so that you can understand where are the portions which are giving rise to reflections, etc. That's the best part of it. So we just take a simple case that if there is a transmission line like this, we connect a source and there is a load over there. So once you connect it, that switch, then it will send a pulse in the transmission line, which will propagate over the transmission line, get reflected from RL. If RL is different from Z0, there will be a reflection over there, reflected pulse will come, move towards the left, and then if RS is different from Z0, again there will be reflection. So there will be to and fro movements of this one. And finally, after some reflections, it will come to a steady state. So just like here in the lower one, how the voltage as a function of time at the middle of the transmission line. Similar type of behavior you will get at various portions of the transmission line. And finally, you will get some steady state distribution. And that is the common feature in all FDTD techniques, whether it is a transmission line or whether it's some other geometry. So that's a pulse propagation. So basically what we are doing is we are studying the change in the shape of the pulse due to reflections as it propagates in the device, and this we are trying to simulate. The pulse is allowed to propagate until a steady state is reached, or incremental change is less than the pre-specified value. Okay, that's when you are using, let's say, software like PSP Micro Studio, which is a finite integer FDTD similar to it. Not exactly a FDTD program. Instead of, although it is in space, it is a finite difference, but in time it is called finite integration one. But overall process is similar to that one. The pulse propagation is there. Now the question is that when the pulse starts from a time t is equal to 0 from 1 end, and finally it reaches the steady state. What is the elapsed time, maximum value of elapsed time t? How to find out that time? Because finding out that time, or in terms of the time steps, that is very important. Okay? Now, the steady state value of the field distribution of the device is used to determine the desired characteristics such as S matrix, radiation pattern, etc. And the animation we generate as the wave propagates, basically generates animation, is used to determine the points and magnitude of reflection in the device and may be used for analysis, modeling, and design. Looks simple, so as the simpler problems are concerned, that you can find out the points of reflection which can be used for analysis, modeling, and design. But its importance seems to be more and more when we are trying to work out the complex problems. Let me take an example. Say, for example, there are lots of research scholars these days who are working on ultra-wideband antennas. Okay? 3 to 10 gigahertz, they design the ultra-wideband antenna, start with some simple structure, and then make modification in this one. In a, you can say, without knowing what's happening over there, because the knowledge is incomplete. So they sit with the simulator, make changes, and ultimately they come out with the product they are trying to design, most of the time. They just fabricate it, test it, and then send it for publication. But most of the time we find they don't know and they are not able to provide what's the reason for that. And that's what we are trying to understand now when I say that the animation, see, they are trying to design those products like ultra-wideband antenna. They can use CST Micro Studio, they can use this MOM-based method, or they can use any other this simulation method, computational method, they can design it. But what I find is that FDTD method is an extra advantage because it produces the animation, and if you follow that animation and if you can analyze it, maybe then you may be able to use that animation or those points of reflections, etc., for analysis, modeling, and design, or you can understand. But it's not, I don't think that it is that easy. I'm trying to work on that problem these days. Okay? Try to understand the physics of the problem and then try to model all these couplings, etc., so that one can get into the design process. What happened? So these are the governing equations for FDTD. That is, we start with the Maxwell's equation in the differential form. They are discretized to obtain the governing equations. Now, when you are trying to discretize the Maxwell's equation, basically in the Maxwell's equation you have the derivative with respect to space and time. And those derivatives your computer cannot accept. So you turn these derivatives into the finite difference form. Like it's given there, that the first derivative function f with respect to u. How you write it in the difference of the two. And one approximation on the right side is there, that there is another term O which is of the order of second order delta u. So there is already an approximation over here. So you cannot get an exact solution unless this delta u becomes 0. So finite difference approximation is employed to replace those derivatives by the difference of two terms. Okay. So taking an example we are trying to derive the governing equation for the TEM wave propagation. The TEM wave propagation is has components Ey and Hz propagating in the z direction. So these are the two terms for the derived from the Maxwell's equations. One is Ey in terms of Hz, other is Hz in terms of Ey in derivatives, etc. These are the two equations which describe the propagation of a TEM wave. So right now they are in the differential form. So we convert them into the finite difference form. These are the corresponding finite difference forms. So basically, it involves the discretization also. Because you see that here we have the y component electric field on the top equation on the left hand side, component of electric field at index I. That is, we have one dimensional, we are discretizing it along the direction of propagation, and that index is given by I, the space index. And the time is also discretized because we have derivative with respect to time. So time is also discretized, and the corresponding index is n over there. The components of electric field or magnetic field, Ey and Hg, they are function of I and S. So the first equation is the finite difference approximation of the first equation, and second is the finite difference approximation of the second equation. So it involves Ey, Hg as the basis. Another thing over here is, in fact, we are coming to that part also in the next one, the placement of the field components. How do we place the field components? We have, right now, we have only two components over here because it's a simple problem. Ey and Hg are there. But in a complex problem, 3D problem, you will have all the 6 components. 3 components of electric field, 3 components of magnetic field. So how do we place these field components? So, say for example, in this particular problem, after discretization of the magnetic field, we produce nodes at the junction of the grid lines. Here it is simple there, so we create the nodes over there. The electric and magnetic field components are not to be assigned at all the nodes. We create a nodes over there. In principle, we need to find out the electric and magnetic field components at each and every point in a problem. That means that we should find out these field components at each and every node. But we don't do over this. We find the electric field at some nodes and magnetic field nodes at in-between places only. Just to save the computer time as well as computer memory. Okay? But the thing is that any placement of field components, it cannot be arbitrary. The placement of field components must satisfy the Maxwell's equations. It has to be consistent with Maxwell's equations. So we employ the staggered grid geometry to save computer time and storage. That's what we have over here. The staggered grid is there. That is 1, 2, 3, those ones with vertical arrows. Those are the y component field, and in between those fields, there are the magnetic fields Hc. And the separation between two consecutive nodes, we call it as the delta X in this case. So here the electric and magnetic field nodes are separated by half space step. Okay. Similarly, the electric and magnetic field components are computed alternative at n delta and n plus half delta instance. This is just to save the time and memory. There is no other justification. Because the thing is that if we want to compute electric field and magnetic field at all the nodes, if we compute these values at all values of nt and n plus half delta t, then the storage required will be twice of that. And similarly, the time requirement, the time will also become double. But this way, We are saving the storage, we are saving the processing time, and in between, if at all, we need to find out the, let's say, the electric fields, wherever the electric field is not known, we have not calculated earlier. So we can use the averaging to find out the field at those points. That's what we do. Okay, this is the source. So here we have two grids. One is the grid for the electric field components, and other is the grid for the magnetic field components, and the two grids are separated from each other by delta x by 2. Okay. For 3D case, we have what is called a V cell, the most famous one, which was I think 1965 or so. It was formulated by one scientist Yi, but after about 15-20 years of that, people started using it for everything. And you can see the placement of electric and magnetic field components, how it is alternative to each other, and the Maxwell's differential equation and integral equations are satisfied for each and every phase of this. Okay? That is, E nodes are surrounded by H nodes and vice versa. And this placement of nodes in V cells satisfies the Maxwell's equation in differential form as well as the integral form. So now that you have a geometry, you have discretized it, you have created nodes, you have created cells, you have assigned the electric and magnetic field at various places so as they satisfy the Maxwell's equation. Now the next part is, or the most important part is in FDTD is the wave propagation or the space-time marching of fields. How does this space-time marching of fields is simulated in FDTD? We take it granted so far as the wave propagation is concerned, so far as the analytical methods are concerned, that if there is a wave is an excitation sound, then this excitation is to propagate, okay, with time. How do we simulate in FDTD as such? Or how does it get generated? Okay, these are the same example is there. We have those basic equations, then there is a finite difference form is there, which are already come across. These are the two equations in the discretized form. Basically, these two equations, now we have put it in a slightly different form. The upper equation, which says that the magnetic field, Z component of magnetic field at n plus half time step and at a node I plus half is equal to, can be obtained from the magnetic field at the same node but at an earlier time instant, n minus half. And the other two terms are the electric fields, electric field components at I plus 1 node and ith node at time instant n. That is, we can find out the magnetic field from the earlier values of the magnetic field at the same node plus the electric field components at the earlier time instant, at the earlier nodes. Okay. Similarly, field Ey at n plus 1 time instant can be updated from the electric field at the nth instant plus the magnetic field components at n plus half time instants and at earlier nodes I plus half, that is these two nodes I plus half and I minus half, they are surrounding these nodes ith node. That's how you will be able to obtain these two equations represent the space-time marching. That how we at a later instant and at a later node. Okay, that's space-time marching of the fields. Now this shows, view graph shows the graphical representation of the space-time marching of fields. In fact, these things are very important. Unless you understand this basic process through various means, you won't be able to get the sense of FDTD. So it shows on the this x-axis, we have the time at n minus 1, n minus half, n plus half, n plus 1, that's the time instant, and delta t. On the y-axis, we have nodes, I plus 1, I plus half, I, and I minus half. So it shows there that at those three arrows, that hz at n plus half, it is the same equations we are putting in graphical form, that hz is obtained at n plus half at I plus half through ey at I plus 1, ey at I, and hg at the earlier time instant. Similarly, later you go to the next time instant, you can find out ey from two components of two values of hg and one value of ey. So this is the graphical representation of these equations. Sorry. Okay, it doesn't come well. This was the same thing in a tabular form. The value is calculated and the excitation was included over there. Anyway, so I hope that now you have understood what is the space type, how the space type marching of the fields, or how the wave propagation is simulated in FDTD. Okay. Now there are errors, etc. we are talking about, because any computational method is going to give you an approximate solution. One type of error was coming due to, say for example, in this case, when you replace the derivative by the finite difference form, there is an approximation over there. And this approximation gives rise to what we call it as a numerical dispersion. Numerical dispersion is quite common in most of the computation methods, except in MOM, methodology. So here in this case, in FDTD, numerical dispersion depends on two parameters. One is the cell size, delta x, and other is the time step. One is space step, delta x, and the time step, delta t. Because you are taking the derivative with respect to time, you are taking the derivative with respect to x. So any approximation of that derivative with respect to x will give rise to error associated with this finite difference approximation in x. Similarly, the time derivative will give rise to an error, and that error will depend upon the value of delta t. And we call it numerical dispersion, because even if you have a medium which is dispersionless, these errors will create a solution which is going to have a dispersion behavior because of these errors. So that's why we call it as a numerical dispersion. Actually, it is not an actual dispersion. Medium may be dispersionless, but the solution is the dispersion. That's why we call it as a numerical dispersion. And the amount of numerical dispersion depends on both values of delta x and delta t. As delta x and delta t, this size, this space step and time step approaches 0, the corresponding error or the numerical dispersion is also going to become smaller and smaller. Okay? So now how do we find out the numerical dispersion? Let's take a simple example. So for example, we have a plane wave, we want to find out the solution for a wave equation. This is a plane wave solution for this wave equation is of this form. In the discretized form, it will be a solution of this type. Okay? And we plug in this solution in the discretized form of the above equation, and this will give you a dispersion relation which is given at the end. And you can see that this dispersion relation will be an exact equation, the static dispersion in that case. We can put it in this form, trying to find out the phase velocity, normalized phase velocity as a function of delta x, etc. Where the alpha in this equation is called the stability factor, and depends on both delta t and delta x is defined over there. Now, when we present this equation in a graphical form, on the y-axis we have normalized phase velocity, on the x-axis we have delta x normalized to lambda. That is, the space step is normalized to the wavelength, and you can see, and this parameter is alpha. Alpha is equal to 1, alpha is 0.75, 0.5, 0.25, etc. And alpha is basically the ratio of C delta T over delta X. So delta, the effect of delta T is coming through alpha, and the effect of delta X is straight away there. And you can see that as the value of delta X increases, the space step increases, that along the x-axis, the expected value for the free space Vp by C is supposed to be 1, dispersionless space. But it is becoming less than, Vp by C is becoming less than 1 because of the numerical dispersion. And as the value of delta X increases, the numerical dispersion increases. But strangely, even the value of alpha, which is C delta T by delta X, even if you take small value of delta T, making alpha smaller doesn't help. The dispersion, numerical dispersion increases. But there is another strange thing happening over here, that large value of alpha, alpha is equal to 1, is giving you the exact solution. This alpha is equal to 1 is called the magic step in FDTD. That is, for alpha is equal to 1, the error associated with this, you can say the final difference approximation on the left side and right side, they cancel each other and we get the exact solution. Okay, but there is no such thing. There is a magic time step for 1D problem, but there is no such magic step for 2D problem and 3D problem. Okay, so this is the numerical dispersion. That is a feature of almost all the computational techniques. Although numerical dispersion in almost all the cases that becomes smaller and smaller as the cell size decreases. Optimum, yeah, we are coming to that. Another feature of FDTD solution is what we call it stability of the solution. And here the stability is conditional. And this stability depends upon delta T, the step size in time. And there is a theorem about this one, which we call it a CFL, stability condition, not the compact fluorescent lamp. CFL stands for current, static, and that is stability condition. And that is that time step delta T should be less than delta X divided by the Vmax. That is basically, this condition means that your grid should be causally connected. You cannot have a value of delta T greater than the time taken by the wave to travel from one node to the another. If you violate that condition, then you are going to get into the instability problem. Huh? No sense. And probably people try to do it. Why do we want to increase the value of delta T? Can you give me any answer? Anybody? Why do you want to increase the value of delta T? We want to reduce the number of time steps. We want to have a quick solution. Because otherwise, in most of the cases, when you are trying to find out the FDTD solution, you may require 18,000 to 20,000 time steps. You have to update the field distribution 18 to 20,000 times. And if we can get the solution 10 times that time by increasing the value of delta T, who wouldn't like to do that? But if you try to increase delta T arbitrarily, then your solution becomes unstable. Okay? So the delta T value has to satisfy this condition if you don't want to have instability in the solution. And how do you find out the instability? Okay. Now first we are taking an example. the propagation of rectangular pulse in space for different values of alpha. Delta x is equal to 1.5 millimeter pulse width per 500 picosecond. So for example, we have a one-dimensional problem. We have a grid, just like we were talking about the discretized one, and we have nucleated a rectangular pulse. We are just taking first the case of alpha is equal to 1, which is a magic time step, and the pulse width is shown there. And here you can find that the pulse shape is exactly rectangular as it propagates. But the moment you make alpha different from 1, next one is alpha is equal to 0.99, slightly less than alpha is equal to 1. And you can see the pulse shape has changed. Okay? At the input this thing, when it is rising as well as when it is coming down, there is a ringing there. Because of, this ringing is there because of the dispersion. Okay? Alpha is equal to 0.5. You can see because of the numerical dispersion, the ringing has increased. But the solution is still stable. Right now, we are not talking about the instability. We are just seeing the effect of numerical dispersion on the shape of the pulse for different values of alpha. Now we want to introduce instability and see what instability does to the solution process. Intentionally, we have increased the value of alpha greater than 1. It is 1.00004. And at n is equal to 480 times that. And we have used the Gaussian pulse, because in the Gaussian pulse it is easier to see the instability rather than in the rectangular one. The Gaussian pulse has reached some position in the grid, but on the lower side, left side of it, there is a slight amplitude there. Instead of being straight, our initial pulse, Gaussian pulse was straight and then it was like this. But when it propagates in the grid, alpha is greater than 1, there is a certain amplitude over there, n is equal to 480. That is 480 times that. Now we increase, for the same case, we have made it n is equal to 550. That it is propagating forward. When it is propagating forward from 480 to 550, the main pulse remains like that, but the tail portion, the amplitude has increased. The tail portion of this amplitude of the tail portion will keep on increasing as you increase the value of number of time steps. And that is what is called the instability of the solution. It should not have been there at all. And the reason for this one is that in this case, the instability is marked by non-zero amplitude at the trailing edge. It is due to higher frequency components traveling at slower speed. Because they are traveling at slower speed, so they appear on the trailing edge over here. Okay? And this amplitude grows with that. That's how we find out the instability of the solution. So, what is the solution? So, we have talked about the conditional stability. Is there something what we can call it as unconditionally stable solution? So people have found out this conditionally stable algorithm puts an upper limit on the value of delta t. Therefore, large defined the total number of time steps before this steady state is reached. Solution is unconditionally stable FDTD algorithms. Now these algorithms are available where you can increase the value of delta t, but those solution algorithms require some extra steps. So matrix solution is required in between as an intermediate step, but those solutions are available. Okay. Okay. Now I have an example on it. I don't know how much time is there. So I see. Can we get any record? Pardon? Okay. Yeah. In fact, I had a video clip on this one. Somehow that video clip is not working. So this is on FDTD simulation. The same problem, reflection at an air dielectric interface. So on the left side, those lines are marked. We have air dielectric. On the right side, we have epsilon r equal to 4. And this is a Gaussian pulse which is propagating on the grid at n is equal to 400. So this Gaussian pulse hasn't reached the interface so far. Okay? I have the video clip, but somehow that's not working, but it would have been very interesting to look at. And now you see that n is equal to 700 steps. That was at 400 steps. It hasn't reached the interface. As we increase the time, make it 700, it has crossed that interface, and at the interface it gets reflected, and you can see the reflected pulse, inverted one, because the reflection coefficient is negative over here. On the right side you have the transmitted pulse. Okay? And the animation produces all these things. Similarly, if the same grid is excited with CW excitation, left side we have the incident wave. This CW is at 500 megahertz. Epsilon at n is equal to 800 times step. So this wave propagates, it's a CW1, and as it reaches the interface, it gets reflected. So in the middle portion, you have the reflected wave plus the incident wave. That's why the standing wave is there in the middle portion. On the right side of the interface, you have the transmitted wave. And the dielectric which you are using is a lossy dielectric. And due to the lossy dielectric, you can see that the transmitted wave, the amplitude is decreasing exponentially. So you have a epsilon r is equal to 4 and sigma is equal to 0.001. From this behavior, you can find out if you know epsilon r, etc., sigma, etc., you can find out the phase velocity in that particular medium, the dielectric medium. You can find out the alpha value also. Or if you know the alpha value and phase velocity, you can find out the parameters of the dielectric. Just like when you are working with any wave propagation in a lossy dielectric, or when you are doing the experiment in your lab, if you have this standing wave pattern, etc., you can find out all the parameters. Same thing, we are simulating over here. Now we are coming to the rule of thumb for cell size delta x. The rule of thumb is that, first of all, if you reduce delta x, your accuracy will increase, the accuracy of the solution will increase, but your number of nodes, the accuracy of the solution will increase, but the number of nodes will also increase. So that means you will require more of computer memory as well as more of processing time. So how to compromise between the two? In fact, we are coming to the rule of thumb. The value of delta x depends on the frequency, because normally we put it as delta x by lambda, normalized value. It depends on the material properties and the expected field distribution in the cell, these three parameters. But as a rule of thumb, it is delta x should be around, we can say lambda by 20 for 1% accuracy. Lambda is the wavelength in that particular medium. For 2% accuracy, should be around lambda by 10. And if you want to have crude approximation like 5% accuracy, you can have even lambda by 5, bigger cell size. For 3D cells, the above rule will apply to the largest, no, it should be applied to the smaller dimension of the cell, not the largest cell, for the 3D cell. Rule of thumb similarly there for delta t also. That is, after selecting the value of delta x, after selecting what is the cell size, then we have to find out the value of delta t which satisfies the CFL condition. And normally we put it in terms of a parameter which we call it alpha, or the stability factor. And in order to take care of that, your geometry may consist of different dielectric mediums, etc., with different phase velocities. So as a rule of thumb, instead of keep changing this delta t all the time, we put it in terms of some particular value of alpha, and alpha is equal to 0.5. It's taken more or less as a thumb rule. Alpha is equal to 0.5 means that once you have selected delta x, then you can find out what is the corresponding value of delta. Okay? So I'll just give a simple example that how much time steps will be required for stability. That if you have a linear resonator of length L, which is lambda by 2, and in this case we have taken it to be about 15 centimeter in free space. The one-way travel time for the wave will be T is equal to L by C. It will come out to be 5,000 picosecond. And since the wave undergoes resonator type, undergoes reflection a number of times before the field stabilization occurs, the elapsed time may be, as a rule of thumb, may be taken as 20t, 20 times one-way travel time. So you can put it in terms of n delta t is equal to 20t, which means 100,000 picoseconds, and for about 1% accuracy to take delta x equal to lambda by 20, which is 1.5 centimeter, and assuming alpha is equal to 0.5 with all those things, it will come to anywhere in this case 4,000 time steps. But most of the cases, we have time steps which range between 16,000 to 20,000 time steps before this stabilization. That gives you some idea of height. Next is that we have got now the data. We have generated the field distribution over the grid and as a function of time. And we have the data in terms of function of x, or you can say function of I and delta t, etc. You have the information in the time domain, and you want to have the convert it to the frequency domain information, then you use the DFT, etc. And get the frequency domain. And depending upon the value of delta t, you can find out the frequency resolution. So, this is the same example we were talking about. In this case, we have taken n is equal to 16,384 time steps with delta x equal to 1.5 millimeter, delta t 25 picosecond. So, therefore, the frequency resolution in this case was around 24 megahertz. And from the data, we calculated the reflection coefficient at the air dielectric interface. And this compares with the theoretical value. It's a simple, it should have been minus 1.3, but this method is giving a value which is around minus 1.3, but there is a slight, as you increase the frequency, instead of being constant, there is a slight increase is there, and that's because of the errors, etc. Theoretical value should have been constant as a function, independent frequency for that particular example. Now there are some other important issues which we couldn't address over here, because I have been talking about only the basics of FDTD. So we have not introduced the excitation in the grid. There has to be excitation. We have not talked about the pulse design, how to design the rectangular pulse, or normally we prefer the Gaussian pulse, because there is a lot less wastage of the frequency components. Only are addressing the important component, frequency components, or the important frequency region. But if you go to the rectangular pulse, then you will be unnecessarily collecting information for those frequency components of which you are not using at all. Yeah, monocycles also used. We are now talking about the absorbing boundary conditions. Absorbing boundary conditions is a part of any numeric computational technique. So we can put it in terms of either a differential equation, or we can put it in terms of PML, perfectly matched. Then time domain modeling of the lossy dispersive materials, because we are working in the time domain. In the frequency domain, you can model the lossy dispersive material easily. But how do you model it in the time domain? That's still a problem. You want to have finally you want to have information over certain frequency range. You have information how this material property is varying with frequency, it's epsilon value or sigma value, how it varies over the frequency range. But here we have to express all those things in the time domain. It involves convolution, etc. So that's a very sticky process. Unconditionally stable algorithm, they are there, but we are not expressed. And for the triangular tetrahedral cells for geometry, for computational, other computational techniques. In order to take out irregular shape geometry, we normally use triangular cells for the 2D case and tetrahedral for the 3D case. But there is no such thing in FDTD so far. So that is one limitation of FDTD. Although we can now take care of cylindrical geometries in some manner, or a rectangular geometry, but arbitrary shape geometry, discretization of arbitrary shape geometry in terms of triangular type of cells, that's not possible. So that's the final conclusion. The solution of any electromagnetic problem involves solution of differential or integral equations subject to the boundary condition. Analytical methods are efficient but limited in scope. Computational methods provide a useful platform for product development. That's what most of these students, research scholars do these days. Basics of FDTD such as discretization of Maxwell's equations, time marching of fields, thumb rules for delta x and delta t, stability of solution, numerical dispersion, reflection at an interface, and extraction of frequency domain information from time domain were discussed for the 1 days. And the use of computational methods will be used as a supplement in electromagnetics education, which will make the subject interesting and will help in visualization. That's all. Thank you very much. Any questions? It was one-way traffic so far.
The session is open for discussions, please.
Okay. No. There are so many references. It's very difficult to list all of these. In fact, I must have taught this subject more than 25 times. I generated my own resources also, but I think for me also the first reference so far as FDTD was the famous book by Ellen Kaplan. Okay. So I think I would say that's the best reference.
I have 2 comments. With your kind permission.
Please, there is a...
Actually, in this country, find hardly 2 more people, or any more people who can address computational electromagnetics. That is the alarming and shape of this country. So I think it is the proper forum where you can understand the importance of this topic. Suppose a lawyer is dealing with laws without understanding Constitution of India. It is a kind of thing we are doing electromagnetics, but without understanding the computational part or the real physics embedded in the electromagnetics. Suppose you are dealing with, I'll just address this issue, always you are using HFSS or many other codes. So in this context, I'm coming to this point that observing boundary condition or PML is very important part. I think you can add a few more about ABC.
Yeah, ABC, in fact, there are 2 types of, I think, boundary conditions, absorbing boundary condition, or we should say, how do we terminate the geometry? Say, for example, you are trying to analyze a geometry for antenna, which is naturally radiating in space, or you are trying to analyze a circuit which is using the printed lines, etc., which is bounded in one particular direction but not bounded in other direction. Naturally, there are going to be radiations from it. And when it is open-ended on some dimension, on some direction, there is an infinite space around it. You cannot use infinite space for your simulation. You can use only the finite space. Otherwise, from where do you get the memory? How do you process it? So you have to make it finite. And in order to make it finite, you have to limit the space. Either you limit the space putting what we call it as the absorbing boundary conditions. That is, somewhere you draw the line, and on that line or boundary, you express the boundary condition in terms of differential equation type, which we call it as absorbing boundary condition. That's the analytical type. Or you limit the space by putting the absorb, like you do in the anechoic chamber. That is, you put the absorbers, actual absorbers over there, so that when the wave is coming out, or some radiation is coming out from this geometry, either from an antenna or a circuit based on, let's say, microstrip line, etc. That wave, when it is incident on this either absorbing boundary condition or an absorber, it gets absorbed over there without getting reflected back. That's the purpose of the absorbing boundary condition. You want to limit the infinite space to a finite space. And the challenge in these absorbing boundary conditions or PML is that how to make it reflectionless, that they should not reflect. They should allow the wave to propagate or the wave to be absorbed, which is incidental. So reflection should be minimized, and secondly, at the same time, they may have the required bandwidth of the problem you are trying to analyze. If you are trying to design an antenna which is, let's say, ultra wideband from 3 to 10 gigahertz, then absorbing boundary condition should also work over that frequency range. That's the bandwidth as well as the reflectionless condition. That's a real challenge. But these days it's available, it is there in all the softwares. And most of the softwares put it in terms of what you call it is PML, perfectly matched layers. So it will be in terms of number of, yeah, there are problems, no doubt, but there is a progress. But first you have to understand that what the concept is and what are the reasons for not behaving it as you think that it should behave. Okay.
If there are no queries, we have a small request from the organizers. Yeah, one last query, please. Yeah, from this bench. Please.
Yes. Okay, wastage of the frequency component. Okay. What I said was that when you are, let's say, trying to analyze any device over, let's say, 8 gigahertz to 10 gigahertz frequency range. So you should design a pulse such that most of the frequency components of that pulse should be in the 8 to 10 gigahertz frequency. Because when you are using FDTD, you are not working in the frequency domain, you are working in the time domain. You are designing a time pulse, either in the form of rectangular pulse or a Gaussian pulse or something like that. And this Gaussian pulse or the rectangular pulse, you have to first convert into the frequency, find out the corresponding frequency components. What are the corresponding frequency components? And you find that most of the frequency components in the 8 to 10 gigahertz range have the maximum amplitude, and outside this 8 to 10 gigahertz, it should have a very small amplitude. But if it is like this, that even the frequency component outside this 8 to 10 gigahertz, they have sufficient amplitude, then you are wasting this thing. You are not properly designing your pulse. In that respect, if you look at the frequency spectrum of the Gaussian pulse, you will find that you can design a Gaussian pulse so that the frequency components between 8 to 10 gigahertz will have the maximum amplitude, and outside it will decrease very, very fast. That's what I try to say, that we are wasting the components or which don't have any value for you. Is that okay?
As for the inputs I have received, there is a small request from the organizers and from our side. There is in view of the fact that there is a slight change of venue for the third lecture, which is going to be session in the adjacent room behind this and towards left. I request the delegates to kindly cooperate with us and continue with any of these further discussions related to this lecture during the off time. There will be a change of venue and the third lecture will be in the room behind this and towards the left. Kindly cooperate with the organizers, please.
One more announcement. This is only for the last session we are going there. All other sessions will be conducted in this room. So there is some overlapping of this booking. So they requested me. I have accommodated, and Professor Misra has agreed to this. One more thing, that all your kids will be handed over to you today before 8 o'clock in your respective room. So be there so that we will avoid this chaotic situation because so many participants. And your bag contains that dinner coupon. Without that coupon, you will not have dinner. So that is. So all of you will have the your kid in your respective room. Secondly, all these lecture materials now available in YouTube channel NITTTR CSD. So your rooms are having the internet connections. So utilize your time more academical way. So Professor Garg will be here for 3-4 more days. So take advantage of his presence because getting him is really tough, but somehow he has agreed for this purpose. And just take advantage of this thing. Let's go to the adjacent room. Just go out of this room. Keep a left turn straight room. There is 180 seats we have arranged there just for this session. Tomorrow